Hey, how about we talk about electricity? Electricity is all around us. It's really important. Lightning, the sparks that you see here, the way that you turn your lights on, your computer, your cell phone, all of that is electricity. There's electricity coming out of your brain that says, ow, my finger hurts. And hey, heart, remember to breathe, okay? There's a lot of stuff going on with electricity, and physics covers that pretty well. So let's take a look and see what we got here. The first thing I need to talk about is electric charge. There are two principal charges. You got a positive charge, you got a negative charge. Of course, that means you could have a neutral too with no charge, but so I guess three, whatever. Positive, negative, and then neutral is when the two cancel each other out. You get the positive charge from protons, you get the negative charge from electrons. You can go a little bit deeper than that if you want, inside the protons, inside the electrons, whatever. But, we haven't gotten to the bottom of that mystery yet. But let's just stop with protons and electrons. That's fine. Protons are positive charges. They have a charge of 1.6 times 10 to the negative 19 coulombs. That would be a positive charge for protons. All you got to do to get the charge of the electron is change the sign to a negative 1.6 10 to the negative 19. And we measure that in coulombs, which is a kind of weird unit. You can see that an individual proton or electron here is 10 to the negative 19 coulombs. So when you get a coulomb, you need to stand back. That is a whole lot of charge, and be a little bit careful with that, okay? Now down here we've got some pictures. If I put two electrons or any two negative charges together, negative charge, you see the arrows? Those are going to push apart from each other. Two protons are going to push apart. They're going to repel each other. But if you get a positive and a negative charge, those are going to attract. There's an attraction there. Opposites attract, and like charges repel. How strongly do they do that, you ask? Well, I'm glad you asked, because Coulomb came along and answered that question for us. This is Coulomb's law right here, where he says the force is equal to K Q1 Q2 over R squared. K is a constant. That's written out over here. And, it's not a bad idea just to write F equals 9 times 10 to the 9. You could put 9E9 if you wanted. The units are nice, so we'll put those in. But you got the first charge. The bigger the first charge is, then the more force there's going to be. The bigger the second charge is, then the bigger the force is going to be. And the distance between them is important. It's an inverse square law, in that as you move them farther apart, the force falls off. If you double the distance, then the force will go to a fourth of what it originally was. Okay? That's Coulomb's law. Super easy to use. No big deal here about the whole thing. I'll do an example or two here. But that is the force between any two charged particles. Here's an example. Find the force of attraction between a ball with a charge of positive 0.2 coulombs and a second ball with a charge of negative 0.3. So you see how it's an attraction there. We know it's an attraction because it's a positive charge and a negative charge. All right, those are going to pull towards each other. And if it's me, what I do is just leave the sign out. I put it in right here. So really the answer should come up negative, but what does that negative mean? We already know that it's an attractive force. We already know that the negative charge is going to be pulled toward the positive charge and the positive charge toward the negative charge. They're going to have that same force on them, like that. So to me, it just makes sense to leave the negative signs out right there. I already know the direction. The negative sign only indicates the direction. And then I could punch this thing up and get the thing. And it's already worked out there for you. But just so you can see the math, there's a whole lot of significant figures and getting everything in order. I would do 9E9. That'll take care of that constant. I need to multiply by 0.02. I need to multiply by 0.03. Whoops, leaving the negative sign out again. And then divided by the distance, 0.5 squared. I will send out a word of caution there that sometimes people see this distance and want to divide it by 2. Okay? We don't want to do that. This is r as is, and I need to take that entire r and square it. The reason people like to mess up and divide that by 2 is because we think of r as a radius. Well, here it's the distance, although I will say that if this was an atom and the electron was moving around the proton like they like to do, then it would be the radius, and that radius would be the entire distance. So even if you are thinking about radius, it would still be proper to keep the whole thing and not divide by 2. All right? Anyway, that's kind of a first example there, and you punch it up and you get a number. You can see this is a monstrous force. 2.16. That's not even enough, is it? I need one more. 216, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. We'll put the commas in here. 21 million newtons. Okay, you do not want to be standing right here because it's going to turn you into applesauce. All right, that is a whole lot of force. This is a big charge. That is a big charge. They are not very far apart. So there's, kind of 3 factors there going on. And 0.02 coulombs doesn't sound like a lot of charge, but that's still a whole lot of charge. And you get it, an arm's length away from another charge. There's going to be a mighty, mighty pull between those. So just something to kind of keep in mind. If we had done this with an electron and a proton, the numbers would have been 1.6 times 10 to the negative 19 coulombs. And the proton would have been 1.6 times 10 to the negative 19 coulombs. This one positive, that one negative, but remember we're leaving the negatives out and stuff. So that would knock this thing seriously down and put a really small force on it. You know what? Let's do a thing here. I'm gonna see what that number would look like. Here is the same problem, just with an electron and a proton half a meter apart. And I'll come in here and say 1.6 e negative 19. I'm gonna hit squared just so I don't have to put that number in twice, and then divide by 0.5 squared. And there's the number for an electron and a proton. Okay, so I'll just put EP, something like that, and I already forgot the number. 9.2 e to the negative 28. Okay, that is not a whole lot of force. That's in newtons, not a whole lot of force. But on the other hand, what you got to do is you got to come in here and say, well, what would the acceleration on that electron be? And that's where you'd come in with some first semester physics stuff and say the force is equal to mass times acceleration. So if I take the force and divide by the mass of the electron, here I've got 9.2 times 10 to the negative 28 newtons, and we say, well, that's almost nothing. Let's not even worry about it. But if you come in here and say, fine, I want to divide that by, what is it? I already forgot. Dang it. Where's my... I don't even have it up. If I was a chemistry major, I'd probably remember this kind of number. Sometimes I do, but mass, electron, yeah, right there, 9.1 times 10 to the negative 31 kilograms. All right, 9.1 e negative 31. Where'd my thing go? Yeah. So when I divide this by 9.3, got to get my pen back, sorry. Come here. 9.3 times 10 to the negative 31 kilograms. When I do that little thing right there, I've already got the force in there. I'm going to divide 9.3 e negative 31. I get an acceleration of 991 meters per second squared. That's a whole lot of acceleration. So it's not a large force, but you put that little bitty force on a tiny, tiny object, you're going to get a huge acceleration right there. Coulomb's law is kind of neat. Particle accelerators work on this principle, where we're getting charged particles, and we're running them through magnetic fields, making them go faster and faster. And then when they hit into each other, we'll get this spew of particles that are particles that make up protons and, different things. So it's kind of one way to get down in there and see what's going on inside those charged particles. Anyway, here's a problem right here that says I've got two charges of Q and 3Q, or 40 centimeters apart, and then I want to put a third charge in the middle so that it experiences no net force. Now, they didn't give me any numbers here on the charges. That's okay. Let's let this one be Q, and over here this one will have a charge that's 3 times that, 3Q. So maybe this is 1 Coulomb and that one's 3 coulombs. Doesn't really matter. It's all going to cancel out here. So let's just leave it Q and 3Q and see what happens. But what I need to do is to say, how far away from Q1 do I need to put a new charge, a third charge, Q right here, that it will just stay there. It's just perfectly balanced. Now we're assuming that this one's kind of nailed down and this one's nailed down over here. All right. If I don't hold them in place, then those two will either attract or repel and will move. So we're not letting those move. This guy, we don't want it to move, but what I'm going to do is I'm going to say, well, I want the Q1, and here it doesn't really say, but it doesn't really matter either. Let's say that Q1 is positive and Q2 is positive. They told us that this is Q, so that would make it positive, but even if it were negative, we'll do it positive first. How about that? If Q1 is positive and Q is positive, those will repel each other. There will be a repulsion there. They're like charges, so they're going to push away, and I'm going to get a force going this way due to Q1. So I'm going to call that F1. Meanwhile, Q2 over here is positive. This guy is positive. That's a repulsion. So Q2 is going to push on Q to the left. And I'm going to call that F2, the force that charge 2 puts on Q, like that. And you see how those two forces are going to cancel right there? So all of these problems like this, where you have more than 2 charges, what you're going to do is, it's pretty straightforward. We're going to find F1, and we're going to find F2, and then we want to make sure that F1 plus F2, in this case, equals 0. Now, I should say, you should also know that force is a vector quantity. So if I add a little vector sign here and here and here and here, that gives you a pretty good hint at where we're going with this thing. Because it has a magnitude and a direction, I need to treat these like vectors. That means I need to remember how to add vectors, and we're going to do that right here. But that's our game plan. Okay, this is what we're going to do. First up here, I'm going to find F1. That's simply going to be K Q1 times Q divided by the distance squared. All right, so I'm kind of zooming in on this little piece of the problem right here and saying, well, just tell me what this force is. It's going to be that charge and this distance. We don't know that distance. So I just picked X to be that distance. And if I do like that right there, then that would be force 1. We have drawn this positive, 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 and F1 is to the right. So I'm going to come in here, and you could either put to the right, or you could say at an angle of 0 degrees, whichever way you want. But now it's a proper vector, and I'll put the little hat on there, and that would be force 1. Now we could go and put 99. I don't know what X is. I don't really know what these are. I know it's Q and Q. So let's just leave it like that for a moment and see what happens. Second step, I'm going to find F2, and of course the formula says put in a Q, put in the charge of the first particle, which would be q. Put in the charge of the second particle, which would be q2, and divide by the distance. Now they did tell us that from here to there was 40 centimeters, and I already called this much x. Let's say it's 10 centimeters, right? That's going to leave me 30 over here. I need to do 40 minus x on this side. So here's a 40 minus x, and I got to square that because it says r squared. That's going to be my thing right there. There's f2, and I need a direction in order for it to be a vector. So q2 is going to push this guy to the left, and we normally call that 180 degrees. And if you haven't thought about vectors in a little while, I'll remind you that we always start right here at 0, rotate counterclockwise to 90 degrees, keep going counterclockwise, 180, 270, 360. When I'm thinking about angles, that's the way I measure. Start at the positive x-axis, horizontal to the right, go counterclockwise. Okay, but now we're up to step 3 of this thing, and what I need to do is to say f1 plus f2 equals 0. Alright, and I'm going to come in here and do that, and we'll put it here and here to remind ourselves that these are vectors and we need to add them as vectors, not just numbers right here. So what I can do here is I'll come in, might be easiest, there's a couple ways you could proceed here, but f1 equals negative f2, just add that to both sides, and I could come in here and say f1 is k q1q over x squared, and that's going to be equal to negative, and I got to get my angles in there too. Best way to do that, I suppose, I'll put this in. This is a little bit sloppy and not the way we normally do notation, but just make sure I don't lose it. That was at 0 degrees, and this would be k q q2. Oh, I should have put the 3q in there, shouldn't I? Over 40 minus x squared, like that, and that's at 180 degrees. Okay, 180 degrees means to the left. We could mark that with a negative sign and cancel out this negative sign right there. So I'm going to zap that, and then I don't need this anymore, like that. Alright, there's some other stuff I could cancel here. I have a k on the left and a k on the right. I have q on the left. I have q on the right. So that gets us pretty far down the road. If I'd remembered to put in the 3q, I could have done a little bit more. So let me do that, and that will simplify this thing even more. q1 had a charge of q. It's at a distance of x squared from this point in the middle. And over here I've got q3, and I'm going to go ahead and put in 3q on that. That's at a distance of 40 minus x. Don't forget to square it. Okay, but now you can see that I've got another q on the left and a q on the right. Those are going to cancel. So I'm left with 1 over x squared equals 3 over 40 minus x quantity squared. And probably the easiest thing here is just to cross multiply. If I come in and say 40 minus x squared is equal to 3x squared, like that, essentially I just multiplied both sides by x squared and it canceled on the left, came up here. Multiply both sides by 40 minus x squared, it came up there, like that. So that's probably the best way to do it. Then I need to FOIL this out. 40 times 40 would be 1600. I'd have minus 80x. Oh, that's plus x squared equals 3x squared, like that. All right, and I need to get everything. Probably best to go ahead and subtract that, leave a 0 here. We're looking at a quadratic with x squared and x. So I'm going to get everything on the one side of this. Let's move it over to the right. I don't care. Whichever way you want to go with it. we'll bring 3x squared over this way. So I also need to get this in descending order. If I subtract 3x squared from both sides, it'll cancel over here, leave me a 0. Here's a minus 3x squared to keep it all balanced out. X squared minus 3x squared to be negative 2x squared. I'm going to put that one in first place because I got to get this in descending order. Next up, I've got the x term, which would be negative 80x, and then I've got this positive 1600 right there. Nothing but 0 on the right hand side. All right. Okay, I need to do, my choices here would be to factor, to do the quadratic formula. I could do this on my calculator. I got to do something to crack that quadratic open. I do notice there's a 2 everywhere. So maybe we could divide by negative 2x. Simplify it a little bit down before we get to the quadratic formula. This would be 40x. This would be minus 800 equals 0. Again, just divide everything by negative 2 there and reduce all those numbers down so they're not quite so big. All right, but if I come in with the quadratic formula, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a, then that will give me the number that I need here. B is positive 40, so negative b would be negative 40 plus or minus square root 40 squared. I'm gonna be hard pressed to get all this in here. 4 times 1, let's just leave that one out, times negative 800. Whew. And then I got a 2 times 1, which would just be 2, like that. So on my calculator, I'm going to come in here. Don't forget your little parentheses around the numerator. Make sure that all of this happens before you go dividing by 2, right? And furthermore, when you hit a square root, you're going to get a open parenthesis there. It just automatically does it on your calculator. So you will have to remember to close that one off back here. I don't think I can get that in, but I'll do it on the calculator here for sure. Well, hopefully I will. Okay, I'm going to open up the numerator with that parenthesis right there. Hit negative 40. There's a plus and a minus. Those are going to give me the 2 answers. One when I hit plus, one when I hit minus. So let's try the plus and see what happens here. Square root 40 squared minus 4 times a negative 800. Close the square root, close the numerator. You see 1, 2 parentheses. I got to close both of those. Then divide by 2. And I get 14.6. My units here were centimeters. And that's actually the one that we're looking for. If this distance were 14.64 centimeters, then over here I'd have 40 minus that, which would be, I don't know what, 25.36 centimeters. Okay, that's the point where this one will perfectly cancel out. It's getting pushed to the right by Q1, it's getting pushed to the left by Q2, but right there all those forces cancel out and it stays where you put it. Okay, there is a name for this process. It's called superposition. So I'm going to put that on here just so you never forget it. And hello. Superposition means that I'm taking the effect of 2 different things and adding them up. Okay, and don't forget that they are vectors, so we got to add these as vectors. And the superposition principle says if I take the effect of the first one and add the effect of the second one, then I'll get the total effect. All right, let's do another problem like that. Here's one. It's already kind of hammered out for us, so we can stroll through this one pretty quick. I'm interested in the geometry down in the bottom right corner there. Looks like we've got 2 positive charges and 1 negative charge. These have strange angles. They're not in a straight line anymore. This is a 2-dimensional superposition problem. You could do a 3-dimensional superposition problem. In whatever kind of space you want to put these charges, they push on each other, and we need to know the net effect of the whole thing. So I'm going to see what's going on here. Right here I got 0.04 coulombs, and that's a negative charge. Here's 0.03 coulombs positive, 0.02 coulombs down here. Q1, 2, and 3 look like that. Now they ask us to find the electric force on Q3, and so that's the one that we really want to know what's happening here. That's this guy. So what's happening with him is the big question, and I'm going to just kind of highlight him. I'm going to try anyway. No, I'm not. Woo! Highlighted everything else. Okay, forget that. We want to know what's happening to that guy over there. So I'm going to come in here and think about what the individual forces is. Superposition says break it apart. I'm interested in this guy, and let me get a color you can see here. I'm going to crosshatch him just so that you know, that's the victim there. That's what we want to know. Right here is a negative charge. This one's a positive charge. Those are going to attract. So Q3 is going to get pulled to the left by this guy, and hence I have called this F13, the force of charge 1 on charge 3. Maybe you don't have to have the 3 on there. You can just call it force 1, but whatever you want to name it is fine. I've seen it done both ways. All right, that would be the first force. So I'm going to find F13, and that's already done for you up here. You can see the formula KQ1 Q3 over R13 squared. There's the constant. Oh, and that's part of the unit there. And there's charge 1 and charge 3. And you can see here that I put the negative sign in the formula, but not in the calculation. Again, that's kind of my preferred way because I already know the direction. I know it's straight to the left. And so I put that at an angle of 180 degrees there, and that kind of takes care of it, and I don't need that negative sign. All right. Second step would be to find F23. It's already done for you here. So now I'm looking at this charge and this charge. They are both positive, so they're going to repel each other. I'm interested in this guy, so he's going to experience a force kind of northeasterly there. They tell us that that's a 35-degree angle. So when I get busy and punch this thing up and get the magnitude, then I can just go ahead and put an angle of 35 degrees on there, and that's what I need to know to get that. So here's my first vector. We did step 1. Never mind. Step 2 right there. Now I need to add those two things as vectors. Okay. This is kind of shorthand for it. If you remember the way we added vectors, if you got vector A and vector B, then the resultant is the sum of that. Vector A takes us a little bit to the right, and so we got A sub x down here, and B takes us some more to the right, and when I add those two I get the total to the right. And because this angle right here is adjacent to that, we use the cosine. So right here what they've done is they've come through and said, give me the x components of this. Well, this one's all x, right? This is straight to the left. So there is no y component for the first one. This one does have x and y. So we got to separate that one out. So right there I've got the x component of F13. Right here I've got the x component of F23. Put the cosine in there to say, yeah, I need the angle that's involved, and the adjacent would make me use cosine. Meanwhile, over here, oh, and that's in the I hat direction. Remember those little pointer vectors that say go to the right? And this one says go up, x direction, y direction. So kind of compacted that into one thing just to save a little bit of space here. This one did not have a y component, so it doesn't appear here. This one does have a y component. I need the magnitude times the sine of 35 degrees, and that'll tell me how much it's going up. All right, so now we've got those two numbers. We can see that it's negative and positive. That means that it's going to the left and up like that. And our resultant, the net force, is going this way. I actually drew that into the picture over here. You can see that the Q1 is going to pull it to the left. Q2 is going to push it this way. When I add F1 and F2 or F13, F23, I'm going to get something right down the middle, and that's what we're seeing here. In order to get that, I got to do two things. I got to use the Pythagorean theorem to get this. I'm going to ignore that 10 to the negative 6 because it's in both of them and it's the same. So I would just come in here to get the magnitude. I'd say 4.6 squared plus 8.6 squared, and that's going to be the 9.8 that you see right there. Tack the 10 to the 6 back on, that's fine. To get the angle, I've got to use arctangent. So here is the angle that I'd like to have. Let's call it phi for a second here. I'll give it a different name. The angle we eventually want is over here, so that would be theta. Let's save theta for that one. We'll call this one lollipop here. Okay. Remember that to get that angle, you need to do the arctangent of the y component. That's 8.6 over the x component, 4.6. Again, you could put on the 10 to the 6 here, but you can see how they're just going to cancel, right? So I'm going to leave them off. And that angle right there is a 62. It's already done up for us, but if you haven't done this in a while, then we'll put it right here. And what am I trying to do? Second tangent. I wonder if I'm in degrees here. Good question. I am. Okay. It's always nice to know. Second tangent, 8.6 divided by 4.6. Uh-oh, I don't need a natural log in there. 4.6. There's my 62 degrees. That would be the angle in here, not the angle that I want. I really want to come over here. So it's 180 minus 62, and we did that little fix right there, 118. So there's the magnitude and the direction. That would be the force, and it is a full vector having both parts. So that's another superposition problem there. The geometry makes all the difference. You're always trying to get force 1, force 2, and then add those as vectors. All right. I got one more for you. This one's not written out, so if I went too fast or something on that other one, let's see if we can do this one. This one's on a rectangle. They tell me that the rectangle is 30 meters high and 40 meters wide. And we'd like to do the superposition thing here, finding the force on Q1. This is the guy that we're interested in what's happening there. Okay, so the first thing I would do is say, well, what are these guys going to do to it? Q2 right here is positive. This one's negative, so that's going to attract. I'm going to get a force going that way, and I'll call that F2. Moving on, this one's Q3. Q1, positive, negative, that's an attraction. So it's going to go that way. And positive, negative here, another attraction. So this one actually has 3 vectors, and I got to find those individually and then add them as vectors. So got a little bit of chewing to do here, but it's not too bad. F2 is going to be equal to K. Q1 is 1 Coulomb. Q2 is 2 coulombs. I'm being really sloppy and leaving out the units. We said that distance was 40 meters. So something like that. And when I go 9E9 times 1 times 2 divided by 40 squared, I still get a big number, okay? Because 1 Coulomb and 2 coulombs, even half a football field apart. That's a big deal. 1125 and 4 more zeros. 1125, 1, 2, 3, 4 newtons. And we need a direction here. It's straight to the left, so I'm going to put at an angle of 180 degrees. And now I can put a little hat on that guy right there. There's the first one. I need to find F3, same process. It's K. I'm looking at this guy and this guy right there. 3 coulombs and 1 coulomb. So let's put that in. I need to put the distance in between them. 30 meters this way, 40 meters. They didn't tell me how far it was that way. Looks like I'm going to have to use the Pythagorean theorem. And you probably even already know what the number is, right? Remember the 3, 4, 5 triangle? What would happen if I made everything 3 times bigger? I ought to get 30, 40, 50. Okay? So that's what it should be here, but just to make sure, if I do 30 squared plus 40 squared like that, then sure enough, comes up 50. Okay? So that's the distance that I need to do there. Sometimes you need to fall back on a little bit of geometry or trig or something to get those numbers that you need. They're not always there, but there should always be enough to tell you what to do if you scratch your head enough. Okay, 108 and 5 zeros. They didn't give me that angle either, did they? Well, what I would like to know would be the angle that runs from here. I was trying to get green. Why aren't you green? That's weird. I just wanted to not mess up my drawing any more than I had to. There's some green. And I want to go around counterclockwise until I get to that right there. So what I probably need to do is find this little angle inside here and then add 180 degrees to it. A little bit more trig on that. That angle right there is going to be equal to the arctangent of the opposite. If I'm looking for this angle, the opposite would be 30 over the adjacent, which is 40. And I could come in here and say second tan 30 over 40 is 36.9. Okay, now that's not the angle that I want. That's only this little angle inside here. So I still got to say, well, I always measure from 0 over here. That's our standard. And so I need to add 180 degrees to that. And should be able to do 216.9, I think. Yeah, 216.9. Okay, so that's what we'll put here for the angle on that second one, the force 3. You got the magnitude, got the direction. Got one more of these things. F4 is equal to K. I'm looking at this charge and this charge, 1 Coulomb and 4 Coulomb, so those are the numbers I want right in here. And that distance was 30 meters squared. So I'd have 9E9, whoops, times 1 times 4 divided by 30 squared is a bunch of zeros and a 4. 1, 2, 3, 4, 5, 6, 7 zeros with a 4 marching out in front. So 4, 1, 2, 3, 4, 5, 6, 7, something like that. The attractive force of this positive charge on that negative charge is going to pull it straight down, so we would call that 270 degrees. All right. The last step then would be to add these 3 vectors, and if you remember, there's kind of 4 steps to doing that. First up, we need to say what's r sub x. That's where we're going to use cosine. So I'd have to have the first one times the cosine of 180, the second one times the cosine of that, this one times the cosine of that. Now I wonder if we couldn't make our life a little bit easier here by I guess the numbers, we could take 1,000 off. That doesn't help a whole lot, or even 10,000. Should have picked some numbers that didn't end up so big, but I guess we can see them all here. So if I do 1125 and 4 zeros times the cosine of 180, close up your cosine, plus 10, 8, and 5 more zeros, 1, 2, 3, 4, 5, cosine 216.9 plus 40 million times the cosine of 270, then that'll go ahead and add all those parts right there. I get a negative number. Why is it a negative number? I'm looking for the x component. This guy pulls it to the left. This guy pulls it left and down. This one just down. Nobody's pulling right. So yeah, it's going to end up a negative number. That makes sense. And let me see if I can put that here. Negative 198865. I can't remember numbers. It's just a problem. That's why I'm in physics instead of biology, because I can't remember anything. 886594. History, I'd be hopeless. Okay? I'll go ahead and put a Newton on that because that's what it is. I need to get r sub y. We use cosine for the first step, sine for the second step, and it's kind of nice because now this is already in the calculator. All I got to do is change the cosines to sine. So if I hit second enter and I go back through here and get right there on top of cosine, hit sine, 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 then that'll give me the second answer I want, 584,000. And I'm not comfortable with that. What happened there? Why did that end up a positive number? 180, 216, sure we're in degrees. 180, 216, and 270. Well, let me tell you the dilemma I have here. This one's pulling straight to the left, so it's not up or down at all. This one's pulling down, that one's pulling down. So I've got two horses pulling down and one not pulling up or down at all. The thing should go down. I should have a negative number right there, and I don't. So what did I put in wrong? 180, sine, 216, 270. I messed something up in there. That does not look right. And it's probably something foolish, but that doesn't square with what I expect there. That's suggesting that I get a positive number, which would be up, whereas I had those three vectors. I should get to the left and down. I'm going to put this down and finish this up, but I got some scratching my head here to do. Something, maybe the numbers are so big that it broke it. Something, I don't know. If we pretend that those are the right numbers, then I need to do this, do the Pythagorean theorem, and again that should pull to the left and down, and my resultant should be something like this, and I don't understand why that's a positive number, but I don't want to hold you up. 216 is in the third quadrant, 270 is in the, well, it's on the edge of the third, between the third and fourth quadrant. I don't know, I did something, I just can't see what I goofed up right now. Anyway, we'll go ahead and run these numbers just so you know what to do with it, but something's messed up there. Want to do the square root of this number squared. Of course, when I square it, negative times a negative is going to be positive, so I'm going to just leave that out. 19886594 squared plus 584, this bogus number here, not 0.051 squared, and I would get that monstrous number there. There's 1, 2, 3, 4, 5, 6. Can I just call it 20 million? If I round it to 2 significant digits there, I get something like that. And you know, this has only got 1 significant digit, 1, so I think it's okay. And then for the angle, I got to do 2 things. I got to go find the angle that the resultant. Let me just kind of draw a line in here. If I can get up there, that would show up. Oh, maybe that pink would show up. I'm gonna guess it's somewhere like this, right? You got 2 guys pulling down, so that's gonna pull it down pretty steeply. These 2 are pulling something like that, okay? But we want to find the angle first of all that runs right here. Stop that. That angle, and then really what we want is to come all the way over from 0, so I'd have to add 180 to that right there. So I'm going to call this phi here to begin with. That's going to be the arctangent of the y component over the x component, and I have those numbers here. Second tangent 584,051, the y component, divided by the bottom one here. I like to leave the negative signs out of that as well. I already know which way it's going. I'm looking for an angle between 0 and 90, and that's a 1.6. Interesting. Oh, this is the wrong number. Okay, so again, this is totally bogus here. But 1.7, did I get enough zeros? Maybe that's my problem. I don't know. Probably left out some zeros there because that number doesn't really make sense either, but this one's crazy. So if I add the 180 to adjust, get me in the right quadrant, then that would be 181.7. Of course, this one being positive would really subtract it from 180, but this is messing everything up. But I don't want to waste your time, you know, trying to find it. So that's what you do. Get force 1. Get force 2, get force 3, and then add the vectors, just like we did back in first semester physics, and that should take care of it. I apologize for the typo or whatever foolish thing I did there, but I think you get the idea. Okay? Electric force, good stuff. All right, have a good day.